Hello everyone. In this example, we will discuss how to incorporate safety factors and stress concentrations when performing a fatigue analysis. So in this problem, we have a rod that experiences completely reversed torsion. So what does that mean? It's important that we understand reversed, rotating, and the types of loads that are applied because it affects how we go about doing this analysis and what loads we compensate for and what are our alternating stresses, what are our mean stresses, and how we modify the equation we're going to use. So let's understand what completely reversed torsion is. So let's say we draw a plot of the load as a function of time. Completely reversed torsion means first you twist the rod in one direction with a certain amount of torque, and then with the same amount of torque twist it in the opposite direction and keep doing that, and you achieve a sinusoidal or a cyclic load as a function of time. So if I were to plot the load as a function of time or the torque, it would flip directions sinusoidally about zero. So let's say we twist it in the positive direction or clockwise by positive t naught. And then we twist it in the opposite direction, counterclockwise, by the same amount. So the torque would be negative T naught. So this is what is meant by completely reversed torsion. So it is centered about zero, and the maximum value is T naught, or some torque, and the minimum value is negative T. So the amplitude of, so there is a fixed amplitude which is equal to T naught, and the amplitude is from the center of the wave, or from zero up from the mean value, in this case is zero, to the peak value, which is T naught. So it is machined from steel having a hardness of 150 BHN, and we need to incorporate a safety factor of 2. And using that, we need to estimate the value of the reverse torque that can be applied without causing eventual fatigue failure. So the answer is in the textbook already, 55.8, but I'm going to walk you through how to go about doing this. Now, this is a little different where you have to back solve for the torque. Generally, you'll be given, like for example, in your project, you know the loads, you know the moments, you know the torques, and but you can probably impose some safety factor and solve for diameter, or you can choose a diameter and then solve for the safety factor, which is generally the conventional method you would use, or rather the kind of fatigue analysis you would solve. But in this case, we're going to back solve from the torque. So we'll have to start off with our equation in terms of the safety factor, and then back solve for the stress and eventually the torque. So let's look at what the procedure is here. Now, generally, when there is a safety factor mentioned in the question, I always start off with writing the Goodman's equation. So the Goodman's equation is the mean stress, sigma m, over the ultimate tensile strength plus the alternating stress divided by the endurance limit is equal to 1 over the safety factor. And this is referred to as the Goodman's equation for infinite life. And the reason I say this is for infinite life is because of this Sn term that's in the denominator of the alternating stress. So if I were to redraw the Sn curve, right, it starts off at S3 up on 10 to the 6 and then goes across. So this is your 10 to the 6 and this value here is Sn. So in this case it says, okay, we want to estimate the value of the reverse torque that can be applied without causing eventual fatigue failure. So that basically means infinite life. So that is why we will use that version of the Goodman's equation. Now, what if they asked us, let's say, estimate the value of reverse torque that can be applied to achieve 10 to the 4 cycles, right? So 10,000 cycles. Then, instead of using Sn in the denominator here, we would choose 10 to the 4, go up, and then find the equivalent stress. Let's call that S4. Oops, S4. So then we would modify this equation and write sigma m over SU. So that wouldn't change because that has nothing to do with the fatigue part of it. It's just the mean stress plus sigma A over S4 is equal to 1 over SF. And the way to find S4 would be just as we did in the first example, find S3, right? Because this value over here is S3 or S10 to the 3. S3, find your endurance limit. Even though you're not going to use it in the equation, you still need to find it because then you're going to interpolate by using the log function. So log S4 is equal to 1 over 3 log 10 to the 4 plus log so forth. And then you'll solve for S4, and that's what you will substitute in the equation here to solve for the stresses or the safety factor or whatever you need. So this Goodman's equation can be modified in this case. So equation 1 is for infinite life, but if you are asked or if you desire a life of 10 to the 4 cycles or 10 to the 5 cycles or anything in between 1,000 and 1,000,000 cycles, you can solve for the corresponding strength and substitute that in the denominator of an alternating term. So this is your mean term. This is your alternating term. And this is your safety factor. So this is a good thing to know if you were to ask an exam, or even if you were to design for a certain, if you can anticipate how many cycles your component needs to run for, then you can design accordingly, right? That means it can endure a higher stress because you're going to basically increase the value of the denominator, and that gives you a higher value for the stress to maintain the same safety factor. Okay, so how do we go about doing this? So looking at this diagram that I just drew, right, we're going to have a stress based on due to the completely reversed torsion. So let's look at the stress diagram. So again, if I were to draw it as a function of time, it would start off at some value, 0, and it would fluctuate in a sinusoidal fashion. And this would be your tau max. Right? The reason I say tau is because we're dealing with shear stresses and we only have torsion. So I'm going to talk in terms of tau. Even though I wrote sigma up there, that's just to note that it's some sort of a stress. But we're going to work with tau here. And this down here is your tau min. And you can already tell that tau max is just going to be your 16t over pi d cubed because you have a rounded shaft and it's only due to torque. So what we need to do now for the first part, like I said, I start with the equation. So I'm going to rewrite that equation. So I'm going to rewrite in terms of tau. So I have tau m over SU, right? But this is and now because I'm dealing in terms of shear, I will say SUS. So this is going to be the ultimate shear strength plus tau alternating, that is SN, because we're looking at infinite life, over 1 over the safety factor, which is 2 in our case. So as I said earlier, this is centered about 0, right? So just by looking at the waveform, you can tell that the mean stress is going to be 0. But you can calculate that with an equation as well. So the mean stress is going to be the max stress plus the min stress over 2. And tau max is equal to, so if let's say if tau max is equal to tau and tau min is also equal to tau, let's call it tau naught, right? Then we have sorry, negative tau naught, right? Because tau min is below the 0. So it's going to be tau naught minus tau naught over 2. So our mean stress is 0, which makes sense because it's centered about 0. And the alternating stress is your maximum stress minus your minimum stress divided by 2. Again, that's the amplitude of your waveform. That's equal to tau naught minus tau naught over 2, which is equal to tau naught. So because tau mean is 0, this term drops out. So what we're left with is tau alternating over Sn is equal to 1 over Sf. And we can say that tau alternating is just tau naught over Sn equal to 1 over Sf. So if we find Sn and we know Sf, we have tau naught, right? Or do we? So tau naught is basically the shear stress due to torsion. Now, if we look closely at this diagram, you'll notice that there are areas of stress concentration due to the fillet here and the fillet here. So we need to account for that stress concentration factor as well. So the shear stress here, the alternating shear stress, is going to be some stress concentration factor, Kf, because we're dealing with fatigue. We're going to end up with a fatigue specific stress concentration factor multiplied by tau nominal. And tau nominal is simply our 16t over pi d cubed. And our ultimate aim is to find t over Sn is equal to 1 over Sf. And now, most of us, like if we didn't know the shortcuts, we would try to solve for the Kf due to the 2 millimeter radius or the 0.8 millimeter radius. But as you've already seen in the group discussion work, when you increase the radius of the fillet, you drop the shear stresses, which means that a sharper fillet or a smaller radius is going to be more critical. And because we have torsion across the entire bar, if I were to look at the torque diagram, right, it's going to be same throughout. So the critical point is only determined by the tighter radius, which is our 0.8 millimeter radius. So we can perform an analysis only on this point and still get a decent picture of what the maximum torque should be in order to achieve a safety factor of 2 for infinite life. So let's get right to it. So the first thing I'm going to do is solve for Sn, and then I will solve for Kf. You could do it either way, however you want, and using that and the safety factor, I'm going to solve the shear stress, and then I'm going to back solve for the torque. So the first thing I'm going to do is endurance limit. Sn. So our equation, Sn is equal to Cl, Cg, Cs, Cr, Ct, Sn prime. So let's look for these factors first and then Sn prime. However you want to do it. I usually like to find Sn prime first and get that out of the way. So Sn prime is what? So we said it was 0.5 SU. But this problem does not really give us a value for the ultimate tensile strength. Instead, it tells us what the hardness is. And as I pointed out in the previous example, figure 8.5 tells us that we can find Sn prime using the hardness by just multiplying it by 1.73 if we're dealing with SI units, or 0.25 if we're dealing with the British imperial units. So I can write, so instead of using this equation, because I don't know SU, you can say that Sn prime is equal to 1.73 times your hardness, which is in BHN. So that's 1.73 times 150, or Sn prime is 519 megapascals. Now, another way you could solve it is find out what SU is. And for steels, it's usually SU is equal to 0.5 times BHN to get a value in KSI. So basically 0.5 times 150 is equal to 75 KSI. And then you can convert that to megapascals. There will be a slight difference. I think if you do it this way, you get 517. And this is an approximate value of 590, and you could do it either way, both are right. I just use this because this saves me time because I have to find the conversion factor from KSI to megapascals. Okay, so that's Sn prime, and that is the RR Moore's endurance limit, and it's only dependent on the material. So based on how my component is built and designed, I need to solve for the other factors. So table 8.1, one of the most useful tables in this chapter. So we're looking at torsional loads, right? So we have CL as 0.58. Again, this is purely torsion. If it's a combined loading problem with both bending and torsion, which I will discuss in the next example, the procedure is a little different. In this case, we just have pure torsion, so I can just go down the torsion route. Then the gradient factor. So we're looking at the minimum diameter. Or yeah, in this case, the diameter would be 20 millimeters. And to be more conservative, I would actually take the larger diameter because as you see here, when you increase the diameter, so in this case, if it's less than 10, you have 1, which gives you a higher strength. But if you choose a higher diameter, you get a lower strength. So I'm just going to say, okay, I'm going to choose a 24 millimeter diameter, which falls in this region regardless. So that's going to be 0.9. Then the surface factor, we have to look at figure 8.3. And the question says we have a machined part. So 8.13 is this plot, right? We're dealing with a hardness of 150 and it's machined. So 150 is approximately here. And this is our machined line, machined or cold drawn. So I'll take that to be 0.78. And then again, no information is given about CT or CR. So we're going to assume room temperature and we're going to assume 50% reliability. So I'll just choose 1 and 1. So if I go back to my equation, Sn is equal to 0.58 times 0.9 times 0.78 times 1 times 1 times 519 or 17. And Sn is equal to 105.3 megapascals. So that's the first step to finding the maximum torque. The next thing we can do is find Kf. So Kf, again, like the stress concentration factor from chapter 4 in static loading, is completely dependent on the geometry. So Kf, or the stress concentration factor. But this is in fatigue. And the equation to find Kf is 1 plus Kt minus 1 times Q. So Kt is something we've already seen. It is in chapter 4. Depending on the geometry, you would pick a Kt value given some other geometric ratios. And then Q is something new in this chapter. It's called the notch sensitivity. So first we'll find Kt. So we're going to look at figure 4.35. It looks like this. It's a stepped shaft and it's purely in torsion. So we're going to use 4.35C. And we need to calculate the R over D ratio and the D over D ratio. So let's do that real quick. So we're looking at from figure 4.35c. So we need the R over D ratio. We're taking the smaller radius, which was 0.8 millimeters, and we had a 20 millimeter smaller diameter. So R over D is 0.04, and then D over D is 24 millimeters over 20 millimeters, and that is 1.2. So we can go back to that plot. So 0.04 is here, and 1.2 is our second line conveniently. So that's going to be, I would say, close to 1.7, but not quite. It's actually somewhere here. So I would say this is 1.65. Okay, 1.7 is not entirely wrong, but you want to be as close as possible. So 1.65. So based on figure 1.35, 4.35, KT is equal to 1.65. So now to find KF, we also need to know the knot sensitivity. So now this is going to be in figure 8.24 in your textbook. Now, there are a bunch of things going on, so let's look at it more closely. So we have 0.8 millimeter radius. So that's going to be down here, the notch radius of 0.8 millimeters. So we're looking at something over here. So this is 0.5 and this is 1. So we have 0.75 here, so 0.8. And this is approximate. Usually with Q, it's very hard to get a precise value, so we have a larger range of accepted values. And now it comes down to which of these lines we have to pick. Now, if you're dealing with bending and axial loads, right, you would use these values. But if you're dealing with torsion, you would use these values. And as seen, we're going to deal with torsion, so we'll have to look at what these values are. So the one outside the bracket is the strength in KSI, and the one inside the bracket is the hardness. So what we have here is around 150, right? So I'm just going to take this 160. So there's the 120 line or 116 line. So it's somewhere about here. So in my solutions, I have it down as 0.74. Now you could say 0.72, 0.75, that's fine. Again, we're more flexible with the Q plot because it's very tight and the values aren't very easy to catch. So I'll say it's 0.74. So again, this is Q. So figure 8.23, Q is equal to 0.74. And based on these two values, I can solve for the stress concentration factor in fatigue. Again, this is based in torsion, right? If it were in bending, then you'd have to find one in, if you had a combined loading problem, you'd find one in bending and one in torsion and then put them together respectively with their stresses and then solve. So Kf is equal to 1 plus 1.65 minus 1 times 0.74, and that gives us a stress concentration factor of 1.48. So now that we have the stress concentration factor as well as the endurance limit, we can use this equation to solve for our nominal shear stress. So let's find the shear stress. In problems like this, it's very important, especially when you're doing a handwritten problem, when you don't have ease, to figure out what steps you're going to use to back solve for a value. So write it down somewhere. That way you know exactly how you're going to progress through the problem. Otherwise, you'll hit a dead end, and then if you take the wrong way out, you'll figure out that you're at a dead end, and you might get really confused, don't know what the next steps are, even though you were so close because you went down the wrong path. So again, I highly recommend you maybe draw a flow chart about all the data you need to calculate, so you're not wasting time calculating extra values that you don't really need. Um, yeah. So shear stress, I can use using that equation. So I had Kf times tau nominal over Sn is equal to 1 over Sf. So if I were to isolate tau nominal, I would get the endurance limit divided by the stress concentration factor multiplied by the safety factor. So the stress I'm dealing with is equal to 105.3 megapascals divided by 1.48 unitless multiplied by a safety factor of 2. So my nominal stress in the bar or in the rod is 35.57 megapascals. And finally, calculate the torque. So tau nominal is equal to 16t over pi d cube. Rearranging that, the torque is equal to the stress multiplied by pi d cube over 16. So the torque is equal to, we have 35.57 megapascals times pi times our smaller diameter, because that's what we multiply to find tau nominal, because that gives us the highest value for the stress. So 20 millimeter cube all over 16. That gives us T equal to 55.8 Newton meters. So theoretically, if I were to apply a reversed torque of 55.8 Newton meters on this rod, I would achieve a factor of safety of 2, given the stress concentration factors. The value would be lower if we chose this, for example, the 20 millimeter radius. Now, let's say this were in bending, and you would have a different moment at that 2 millimeter radius and a different bending moment at the 0.8 millimeter radius. Then you'll have to compare the magnitudes of the bending moments and then figure out whether the 2 millimeter radius coupled with its moment at that point, or the 0.8 millimeter radius coupled with that moment at the point, is more critical. So with moments that are not symmetric, or moment diagrams are not symmetric, it's not that easy to figure out what the critical value is. But generally, if it's an exam problem, we wouldn't expect you to find the value or the stress, the maximum stress at each of those features or discontinuities. Instead, what we will make it a more simple problem where we'll have a very extreme radius of maybe like 0.5 millimeters versus like 10 millimeters. So okay, 10 means 10 is kind of unrealistic. So yeah, 2 or 5 or something like that. And it'll be pretty evident which one you would have to choose. So what is important here is to understand what completely reverse torsion is, because if you were to draw it, let's say this is your 0 and you drew it this way, then you would end up with the mean stress, and then you can't drop that first term. So make sure that you understand what a completely reverse torsion is. Completely reverse bending is going to be similar. Repeated, if we say repeated torque, that's what the diagram I just drew. Repeated torque means I load the specimen and then I unload the specimen. So it goes to a maximum value and then it drops to 0, then maximum value, then drops to 0. But reversed means it would go back into the negative axis. So this is basically the procedure that we would use. This is a good thing to know, right? If you were looking for a certain life or a desired life at which it would fail, then you would substitute Sn for the strength at that respective life, and then find the stresses, and then calculate the values you need, account for any stress concentration factors, and solve for the torque.